exchange, before trying to understand the concept of Diffie element key exchange, first you should know what is this discrete logarithm is. Okay, so the basics required for understanding this discrete algorithm I have already explained to you, but still since it's a very long gap, few of you might not remember it as of now, so I'll just take this particular session to just revise the previous concepts and give you a link between those concepts and what is this discrete algorithm, and what exactly its application. Okay, so before I would explain you what is this discrete logarithm, first you should know what is logarithm. So what is logarithm? A logarithm is an exponent. Say for example 2 to the power of 3 is what? 8. Say for example, if I am given with the information that the base is 2 and the resultant is 8, and if I am asked to find what is x, okay, there comes the application of logarithm. Okay, so I'll repeat. Say if you are aware of this base value and the resultant value and you don't know what is the power. Okay, so if you are asked to find the power, there comes the concept of logarithm. That is, see, log 8 to base 2 will give you the exponent. Okay, here comes the concept of logarithm. So we can find one more example here. 3 raised to 4 is what? 81. Log 81 to base 3 will give you 4. So the definition for logarithm is log b to base a is equal to x. Okay, so like most of the time we don't get this whole numbers like 3, 4. Just for making you guys understand the concept of logarithm, I have taken this example, and usually it will end up with points like decimal 0.236, 0.238, 1.023. So likewise the values will be, I mean to say the values will be discrete. It will be between 0 to 1. It lies between 0 to 1, 0 point something, likewise. Okay, so so you can just see log 3 to base 2 is equal to x. 2 raised to x to the power of 2 we should find, so that the resultant value will be 3. Okay, so x, it approximately is equal to 1.58496, so that you will get this 3. Okay, so here comes the concept of logarithm. Once you know the concept of logarithm, next is to understand the concept of group. Okay, so here will these are the concepts which I have already explained to you, but now there is a connection between these concepts and the discrete logarithm. So I have taken again this example to make you guys understand the concept of group, cyclic group, generators. Okay, these are the 3 topics. So just I'll take few minutes so we'll take a set like zp star. So p, it should be a odd prime number. Okay, so zp star, it will contain the values from 1 to p minus 1, and all these values are co-primes with p, that is relatively prime with this. Okay, now please take some time, spend some time, take back your notes, look into the module 1 and try to recall what is relatively prime, what is co-prime concepts. Okay, so now you need to understand the concept of groups. Okay, so when we'll say group, a set as a group, if 2 values in that group, if I multiply, I mean to say if I perform any operation, so here if I take in particular multiplicative group, so in that case if I take any 2 values and if I go for their multiplication, their product should also be placed in the same group. Okay, so then we'll say that it is closed under that operation. Okay, so it should have an identity element and also it should have a inverse value. So these things you know very well. isn't it? Or if all these 4 properties, if this set satisfy, then I'll say that this is a group. Okay, so when will I say a group as a cyclic group? So if it has got at least one element which can bring back all the elements in the set, so in that case I can just call that value as a generator. Say for example, if I take Z11 star, I'll have the values from 1 to 10, isn't it? All these values are relatively prime with 11. So when I'll say that G is equal to 2, it is a generator. If I take this 2 and raise it by the powers like 2 raised to 1, 2, 3, 4, likewise if I just continue until no, to the power of 10, I'll get back all the values that are present in the set. You can just observe here. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and if I continue to raise the power, say G to the power of 11, I'll get 2. G to the power of 12 mod 11, I'll get 4. If I go and continue 2 to the power of 13, I'll get 8. So if I simply go on raising the values, I'll end up with only the answers from the numbers 1 to 10. So hence this set is called, or this set is called as cyclic group. This set initially I proved it as a group. Okay, when I'll call it as a cyclic group, at least it has got one element which can generate back all the values that are present in the set. Okay, so then that set is called as cyclic group. Okay, so here two things, one is cyclic group, the other one is generator. Okay, so this generator plays a very important role. Please remember the concept of generators. Okay, so once you know about this generator and cyclic group, so how to find all these are additional properties here. So in this set, how many generators are there? If you want to know, so then you can calculate that. Please look into your notes. For that you can how we'll find the number of generators, and also how to find a given number is a generator or not. So both the things I have again given an example. Please spend some time to analyze how or when it is called as a generator, how to check whether a given number is generator or not. Okay, so next is so let G be the generator, and yeah, that generator will give you the set. So the last value G raised to P minus 1 will always be equal to 1. So you can see with the example as well. See, 2 raised to 10. 10 is what? P minus 1. Mod 11 if I do, definitely in any of the examples you take, you will get it as 1, and that is called as Fermat's little theorem. Okay. With that theorem, I'll rearrange the values. That's it. Okay, the same set. Now I'll write it as, see, G raised to P minus 1 is always equal to what? 1. So I'll take 1 G square etc. up to G to the power of P minus 2. Okay, so now let Y any number. Okay, I'll take any value that is actually present in this set. So then Y is equal to G to the power of X. Yes or no? Isn't it, guys? See, what do you mean by this Y is equal to G to the power of X is, see, in this if I take 5, okay, 5 is the value of Y. Okay, so Y is equal to what? That is 5 is equal to 2 to the power of 4. 2 to the power of 4 is equal to 5 for mod 11. Okay, that is what we have tried to say here. Okay, Y is equal to G to the power of X. 2 to the power of 4 is equal to 5 for mod is equal to 11. Okay, for mod 11, 2 to the power of 4 will be equal to 2 to the power of 4 will be equal to what? 5. Okay, so for some unique X from 0 to P minus 2, so X is called, so this X, this is called as discrete logarithm of Y. This X is the discrete logarithm for this Y to base G. Are you understanding? Here comes the concept of discrete logarithm. X is called the discrete logarithm of Y to base G. Okay, so here it is very important, the base. Okay, so 3 to the power of 4 mod 11 will not give you 5. It will be a different value. Okay, that is the reason why we say it is not simply logarithm, it is discrete logarithm. Okay, so now interpreting this statement as, see, log y to base g is equal to x. Okay, that is g to the power of x is equal to y in zp star. Are you following? So in zp star, the value of this will lie between 0 to p minus 2. 0 to p minus 2. Why p minus 2 came here? I guess you understood. Okay, so now if the generator is 7 for Z17 star, 7 is generator, you can just cross check, yes, it is a generator. Okay, so g to the power of 14, that is 17 to the power of 14 mod 17 will give you 8. Okay, you have to calculate this. It will not simply, you will never, you can't compute it just like that. You have to, like, 7 raised to 14 mod 17 if you do, so then you will get 8. See, in general, if we were working log say log what 8 to base 2, if I take log, I'll tell you log 8 to base 10 divided by log what 2 to base 10, because there the 10 we know very well. Okay, but here, see here, this is mod 17, it will be operating on what, modular 17, so you can't go for logarithmic applications, don't do that, guys. Okay, so this is discrete logarithm. Okay, 7 to the power of 14 mod 17 is equal to 8, so you have to compute it iteratively. Okay, I'll tell you, it can also be computed in the other way. I'll teach you in the next video that, but now for now just remember 7 to the power of 14 mod 17 is equal to 8. Okay, so the same thing, we can also interpret this as the base is 7, so 7 8, so on raising the exponent value. Okay, that is the discrete logarithmic value is 14 here. Okay, 7 raised to 14 will give you 8 for mod 17 in Z17. So similarly, if you take 14 raised to 10 mod 19 will give you 5. So the definition for the discrete logarithm, so this is nothing but the discrete logarithm problem. So the problem here is to the the difficulty in computing this exponent value. Okay, so when you are aware of the generator and also you are aware of the mod 17, whatever the value that you are working with all this knowledge, now the question will be the exponent. Okay, how to compute this exponent, that is the problem definition what we have, and that is called as the discrete logarithm problem in ZP star. So P an odd prime number, G is a generator for this set, so Y belongs to this set. Okay, so computing this Y itself is a, so even if you have been provided with the knowledge of what is the Y value, okay, what is the resultant value, you will know, but on raising what value to the generator you will get that value, that is the question mark. Okay, so find integer x 0 to p minus 2 such that g to the power of x is equal to y. So this is the definition for discrete logarithm problem. I guess you have understood what is discrete logarithm. Okay, so one thing that we have to understand here is the difficulty in computing this x. Okay, so this difficulty will take this difficulty as an advantage for for cryptographic algorithms. So if p is large and g is generator of zp star, then finding log y g, that is the exponent, and the g raised to x, that x value, to compute it is an intractable problem. Okay, so the security of many cryptographic techniques depends on this. So this discrete logarithm, whatever the issue we have, difficulty in computing x, so that will take as an advantage for the concepts in Diffie-Hellman key agreement and the Egg-Gummel encryption and L-Gummel signature schemes. Okay, so the difficulty of finding this log y to base g is independent of g. Okay, so this the exhaustive search approach, see what I just now explained to you, the difficulty or the iterative approach that you're supposed to follow. Say for example, we have Z19 star. So Z19 star is 1 to 18 numbers. Okay, so G, say if I assume to have a generator 14, so next we have to find what, say for example, if you're asked to find log 7 to base 14, that is, you need to find what, 14 raised to x is equal to 7. You know the resultant value is 7, but on raising this 14 by what power you will get the value as 7 is the question mark. Okay, so for that what I'll do, I'll start from the initial stage, that is 14 square. 14 into 14 mod 19 is 6. Okay, next 14 cube if I want, then 14 square into 14. Okay, so mod 19, so I know 6 already. 6 into 14 will give you 6 into 14 mod 19 will give you 8. So if I follow this same procedure, 14 to the power of 4, 14 square into 14 square, you know what is 14 square in the previous problem. So 6 into 6 will give you 17. Next 14 to the power of, so you will just split the powers so that the computation becomes easy for you. So likewise, if I continue, I'll get the value, the resultant value as 7 on raising this 14 by the power 6. So there comes the answer for me as 6. So you can just look into the complexity of computing this what exponent or the logarithm. So this is discrete logarithm problem. Okay, so say for example, you have been provided log 17 to base 2 mod 131. So what is the value for this? So the value for this is 17. So even this 17 now you will get this 17, the answer is 17 only after performing all these steps. Okay, so getting back or tracking back what is the power to raise to what value will give you 72 is not that easy job. What exactly we are trying to say here is, say if I have transferred this 72 across the channel, okay, communication channel. So the intruder will manage to get the generator 2, the prime number as 131, and also he has been provided with the value as 72. Say if he has managed to get all these three values, then getting this 17 is not that easy job. Okay, here all are small values, then it is really working. Say if you have assumed to take a very big prime number, so then it is not that easy job to get back this power. That is what we are trying to convey here in discrete logarithm. So this complexity in discrete logarithm, so this complexity is taken as the advantage, and that is incorporated in the concept of Diffie-Hellman key exchange. Okay, so discrete logarithm problem is one-way property of modular exponentiation, easy to compute but hard to invert, that makes it of such great use in cryptography. Okay, I hope you guys have understood the concept of discrete logarithm, because this concept will be using in Diffie-Hellman. Fine. Thank you guys.